I must have this. And so I'm using this equation to say the inside of this is equal to this. Okay? And so then I just rewrite it. This is just algebra, and then I try to connect what is inside my initial state for my final outside final state for the electron. Because I want to write what is initially absorbed by the electronic state before the absorption of photon, which is this one here, related to the photon absorption, after the photon absorption, that the electron has already escaped from into the outside of the surface here. And the connection is really quite simple after you do all this little algebra, is that the inside, only the parallel component is concerned. So what I'm trying to say, upshot of all that, is that the parallel component of the initial state, right, inside your solid, right, because you absorb the photon inside the solid, is equal to the final state of your electron outside the surface, minus the surface, the residual lattice and the bulk residual lattice in the parallel direction. So only the parallel component is concerned. Okay, and the perpendicular direction, you don't have any symmetry rule that will. You have no control of the perpendicular direction of what you've done. Okay, so what is interesting is that if you look at a so this gives you a bit of the directional dependency of the symmetry, because you have to follow a sort of rather unique symmetry rule, right? Conservation rule for the parallel component only. So the only thing I want to get you to remember is that only the parallel component of your for electron wave, your electron, need to be conserved, right? It related to each other by some integral of residual lattice spacing, which related to the bulk plus the parallel connection of your the surface and the parallel connection of the bulk. Okay, so that's it. So there's only symmetry rule controlling the parallel component because of this surface effect, and you would see angular dependence of this. Okay, so what's the upshot of all this little math that you see, right? This tells you that the momentum dependence relation between before photon absorption and after photon absorption, for your parallel component. Okay, so that means that there is a symmetry breaking effect on the photoelectron spectrum that you will see. And so what happened then is this. Okay, so let me just show you this, that when you do photoemission, what you got is that you got this band structure, right? So let me go to this. You have this electronic band structure like this. Okay, so remember, the electronic band structure is nothing more. So in the case of free electron, what do you have, right? We also always remember what is a free electron. Free electron, you will get a parabolic band structure, and here it is. So you have a little well here, and you see this little dashed line. You may not be able to see very well. This line that go along here. So this traces out a parabolic structure, and this is the fundamental, right? That if you have just free electron, the free electron structure would be like this. There will be no band gap, nothing, right? Because of the boundary condition that you try to describe in different direction, because of the lattice structure that you have, you create a gap, and you create different band structure, and these are the so you ignore this dashed line, you will have then this little gap in between, and that is the nature of the crystal structure that generate the results of the crystal structure on your electronic band structure. Okay, so they are related. This is why you have structural property effect, and the physical structure of your material directly control the electronic structure in terms of the band structure like this. And this is how, right? Because of the arrangement of your atoms in your solid. So what you got is actually the solid line. And here I'm trying to remind you, I'm plotting here the so-called real zone scheme, right? Meaning that if I don't really need these guys from this point on, because this reduced zone scheme will contain everything. Because I can unfold this onto this side, right? Unfold this out here to get the extended zone scheme, the actual zone scheme as if I proceed to more units. So I'm plotting, remember in the solid I have to specify the direction of my axis, the residual space lattice. And I'm plotting, because at different direction have different periodicity. I'm plotting always from the tau. Tau is always the zone origin, right, from the center, to some direction, and in this case, the x direction. And so there's a certain direction in your reciprocal space lattice that we see before, and that corresponds to moving along a certain direction. And what you see is the band structure that look like this in this particular direction. And so, in the case of photoelectron, then, so you have this basic electronic structure. Now you are sending in a photon, and what are you doing? You're basically effectively, so you look at the, this is 0, corresponding to the Fermi level, right? Where you fill up all your, if you have X amount of electron, you fill up all the electronic band states that you have. So that's the top that defines the maximum electron that you have. Below is all filled state in the case of matter. Above is all empty state. So above here, right? You see this is 0, this is negative. So this is the sort of HOMO state, and this is the LUMO state up here. And of course we haven't considered work function, but so the vacuum level is somewhere. There will be somewhere slightly 4 or 5 volt above the Fermi level generally. And so what happens when you absorb the photon? You're moving whatever electron that you got here. Let's say I have a photon of about 26 electron volt, this much. I'm basically moving this bar across. I'm marching along here, right? I have to march along from one state to another. If I hit empty space, I would not have an absorption. I would not have a photon emission process. So this photon must match the two states as I move along. Okay? So you can see, I can find some field state down here and move it up to this level here. Find some field state down here and move it up. So you can see that the absorption can probe different part of my band structure. And of course, it will depend on your upper state as well. So you could be a very complicated process because as you move up like this, you have intensity, right? It directly controls of how many electrons you have in here, and how many electrons you have in here. Depends on how many buckets that you have, energy level that you have, that you are allowed to put in these buckets. And that, of course, is the density state. So here you have a density state. So what you're probing, in fact, the intensity here is the density state that you got. Okay? So I just tell you that this is just one direction, right? I'm just talking about tau to x direction. Of course, I can do it in many other directions, and the band structure will be totally different, and I will have a totally different electronic structure. And here, I'm just looking at normal emission. I'm looking at my angle, right? I'm looking at my photoelectron directly perpendicular. So here, let me go back to this. I have angular effects in here because of my photon coming in. I have a polarization vector of the photon, which is usually called A vector. The A vector corresponds to the electric field vector, right? The magnetic field vector is often known as the B vector, which is orthogonal to the A vector. Okay. So what controls the intensity that you see is that the polarization vector is important because you have, after all, a dipole excitation of the material. So the A vector will control whether you will have dipole excitation or not. So this direction of the A vector and the normal direction of the surface and the detection So you have three different vectors. You have this A vector, you have the normal, surface normal, which defines the plane of the plane normal of your surface, and then you have detector direction. The detector can move in free space, and you have two angles that you can define the direction of this detector, where you try to catch the full electron. So there are three vectors in effect that you have to consider, because you can move your detector to the normal emission, right? So this is one way that you can sort of simplify. So normally everybody do the experiment at normal emission first, because that will simplify all these little angular effects that you may come in just because of moving the direction.